Okay, welcome everybody to the second track of our day 2 of GeoPython conference. And next up we'll have Joan and Amalia who will tell us something about the European ground motion service data and how it is validated with Jupyter Notebooks. Please start.
Thank you. Yeah, my name is Joan Sala. I work at Sixth Satellite, and my colleague Amalia. We will be doing this presentation in 2 parts. The first part, we introduce some general concepts of this data set of open data. And in the second part, Amalia will show you, we will do a live demo on how we validated this and also the platform. So, the Copernicus European Ground Motion Service belongs to one of the programs of Copernicus, so the land monitoring, which is composed of other layers, as you may know, mostly on land cover, vector, and high-resolution raster layers, and other layers such as the UDEM or the U-Hydro, more thematic, no? Elevation and rivers. So it's a very complete open data platform, and it is all paid by our taxes, no? So it's really interesting to have those. As for the European Ground Motion Service, it's based on Sentinel-1 data, so radar data. It's an active system, not affected by clouds, and the technique applied is InSAR interferometry, able to extract ground motion at a millimetric precisions, and we have in our hands a continental dataset, EU dataset of around 10,000 million time series from 2015 onwards. And this is an operational service, so it will be updated constantly, yearly, once a year with the new time series. As for the visualization, all the scales is normally drawn from red to blue, indicating red indicates subsidence, so the ground is subsiding, green is stability, and blue is uplift, so it is going up. Applications of these are many, from geohazards to anthropogenic generated movement, and climate change adaptation in the end. So here you see examples. There are product levels. We have level 2 product levels, which are in the native resolution of Sentinel-1, so 20 by 5 meter resolution. And these are combined because we have 2 orbits, ascending and descending. We can decompose the movement in horizontal and vertical, and this is done in a regular grid of 100 meters. And as you see, for now, we have published 2015 to 2021, and the 2018 to the 2022 time series, which are the current ones in the viewer. And soon there will be updated to the 2019 to 2023. So this is thanks to a bunch of remote sensing companies, the production consortium, and us, who are in charge of the validation of these data sets. I will show you briefly how we validate this continental scale data set together with geological institutes across Europe. So we have this is basically a graphical abstract of how we validate this. We have 6 validation activities, which I will present very shortly to understand how we validate this, and with mostly in situ data and other type of layers, scientists are able to determine if the service is usable, so it has applicability for what was intended in the beginning, and also we check for consistency and accuracy with known displacements of known phenomena such as the groundwater exploitation or river exploitation in the south of Spain, or landslides in Tyrol areas or France. I will demonstrate one by one how we validate this. So one of the first things we look at is point density. We know this varies in function of the land cover, but we have to check that the data set is uniform, so it has the same performance over the different countries, since it is processed by 4 different algorithms and put together. So basically we determine a fair way to evaluate the density. Amalia will demonstrate this in the Python notebook. We took samples, big samples of urban areas based on the Urban Atlas dataset, and that also Copernicus provides, and it's quality controlled. And we have a total size of the size of Switzerland we took as a sample, if you sum up these 12 big areas in Europe. The conclusions of this is no surprise. The higher the density is in artificial surfaces, where the radar performs better. We have more coherence, less changes, less surface changes, allows us to have more measurement points, whereas in forest or agriculture areas, we lose densities because of the constant changes and the properties of the reflectivity of the ground. Examples of validation. This is the Etna volcano, so we see how each of the sides of the volcano is moving in respect to satellite. Obviously, we have two main active deformation areas. We do clustering to compare to, let's say, the known areas of deformation, and also we were able to capture the 2018 event, let's say, and that proves that the service is fit for purpose. Another example is in landslides. We are comparing this data set to active inventories maintained by the French Geological Survey, VRGM, and comparing the positions of the landslides that are normally surveyed by hand together with the clustering results of the dataset, the moving clusters obtained from EGMS. Here we see on the right side that depending on the orbit, ascending or descending, we're able to cover, and the orientation, we are able to cover different sides of this valley, no? Okay. Other examples is the comparison with other ancillary geodata, normally public layers coming from geological institutes. Here we have a couple of examples. One on the left is Oslo, with anthropogenic movement derived from the construction of the central station. And on the right side we have Lorca, which is a groundwater overexploitation on top of soft soils. And we see well, the correlation with this geological layer, which explains where the movement is stronger. Now, when it comes to precision, we compare with independent GNSS data. That allows us to also evaluate if it's fit for understanding other types of movements, such as seasonality. Seasonal movements are normally related with precipitation and different types of ground going up, making the ground go up and down, or thermal, depending with the temperature, mainly. Other validation, this is with automatic total stations in Tyrol. This is actually a town called Vogelsberg, being affected by a landslide, and we see that the observed displacement can be correlated with the GMS points, which is something, well, you obviously have different precisions temporally and spatially, but it is nice to see this correlation. And last but not least, we have a validation activity with the corner reflectors, which allows us to also evaluate the positioning of the point XYZ, and see how precise EGMS is able to determine the position, knowing that the limitations of that. We have another example in Denmark. The previous one was landslides in Norway, and this one is coastal subsidence in Thyborøn in Denmark. In order to validate this, we have developed a validation environment where the scientists can upload the validation data and also play with it with Jupyter Notebooks, because we want to create reproducible research, so that the users of the service can also check that the service is being validated independently and with reproducible validation methodologies. The whole architecture runs on Terraform and will be pass to the European Environmental Agency at the end of the project. And now we have the demo with my colleague Amalia. So I'm going directly on the platform. The first you will notice is that the vertical product is loaded. On the left, you have the different layers. Oh, sorry, I'm still on the... Am I sharing the full screen or...
You share it, but I couldn't see that.
Yes, but I was on the browser. Or maybe if I turn off this. Sure. Now you see it, cool. So first thing you notice, apart from Switzerland not being covered, because it's outside of the Copernicus program, and that the tiles take a while to load. Yes, this now. So here we see the dataset. Actually, we're seeing the vertical. This red spot here is the city of Bologna, having some problems with overexploitation of groundwater resources. So yeah, the first thing you notice, you have background layers. You can basically, those are WMS services. And we have this vertical product, and that is the 100-meter resolution grid. If I want to activate the ascending mode, might take a while. It's probably due to the bandwidth. Here you have already the points coming up. So it is a 3D viewer, which is nice, especially when working with landslides. On the click, you directly can access. It tells you the point you clicked and which incidence angle, because the satellite is not as we are used to when we're working with Sentinel-2, for example, that is Ortho. This one has an incident angle that depends on the point. And well, this is a place where you would browse through the data, and my colleague Amalia will show you how you can access and download this data. Maybe let's wait until the end, or... quickest.
Okay. You have a question in the meantime?
Just in the meantime, do you expect any difference between ascending and descending?
Yes, so the difference is that you're looking from different sides. So, for instance, in one side, you see the radar object being closer, and the other one, you will see it getting farther away. So when you're interpreting a movement, like in the Etna volcano, ascending will be blue on one side, red on the other, and the other side you would have red and the other one blue on the descending. So radar measures distance, so you see objects getting closer or getting farther away. That's why the Ortho product is by default the one enabled, because it measures vertical movement, and anyone can understand that. But the other two depend on the angles, and they're more complex to understand. It's what we call line of sight.
Can you hear me? All good? Okay. So yeah, in continuation of what Joan was presenting, basically we were working with different validation activities. And let me show you from this platform, first of all, how we can get the data. Because each one of you basically can enter the platform. It requires just an account with EU login, which is straightforward to get. And then once you are in an area that you want to download data, so let's go, for example, in Barcelona we could go, and you're interested in a particular zone that you want to check the movement, there are various options that I invite you to explore in the platform, but now for the last 10 minutes that we have, I will show you directly how you can download them, that you have to select the archive search, and then the data are coming out in releases. We have to different releases. Let's say that I select the latest release, which is from 2018 to 2022, and I select the calibrated product, and then I draw my polygon of where I want the data to be, more or less. So this will give me the available bursts that I can actually select through here to see which one is highlighted and make sure that the one that I will download will be covering the area that I'm interested in. I can also have a more detailed view of the bursts, showing the direction and the ID. So if you know exactly the ID that is covering the area that you're interested, you can directly download there. But also if you select from here and you go back to the browser, it is highlighted the one that you're selecting, like this. But also then, if you want to download all the bursts and not enter into the phase of identifying directly which is the burst that you want, here you can get a list of all the bursts available and use your favorite Python framework to request this data and download them directly. So as Joan was mentioning before, we have the different validation activities, but what we all share is that we used Python and Jupyter Notebooks to construct our analysis. And what we wanted to do was to create notebooks that, first of all, are reproducible, so that everyone can run them and get the same results. But at the same time, the idea was to create reports for each side that we were validating the data to make sure that the end user can actually explore what is going on in that area and maybe also play with the data and do some exploratory analysis of their own, because the planning is for these notebooks to be published at some point. So we have the 12 different sites that we selected across Europe. I will show the example of the notebook from Barcelona. So for getting the point density, we need, basically what we want to check is that we get high density of points in the areas that we expect the technology to work well, and those are the urban areas. While in areas that there is a lot of vegetation or water, we don't expect to have points. So what we need to do this sort of validation is that we need to know the land cover class. And for doing so, we have downloaded the data from Urban Atlas, which is another Copernicus validated product. And here, the legend appears a bit small because I have reproduced the environment for my local machine, but we have it on the online platform of Jupyter Lab. But basically what we do in the report is that we start by taking, from the one hand, we have the data of Urban Atlas, and we visualize how this looks. And the power of Jupyter Notebooks is that we can actually have this diverse input of data. So from one hand, we have text, we have maps, and later we have also the code. So we can combine various texts so that we can have a full and rich report. And we start by seeing a little bit how the distribution of classes looks like. And we show also a chart so that from already first overview, we can see, for example, the classes that they are urban, that are related with urban class, with urban cover. They have warmer colors, and then blue and green are with vegetation. So we already get an idea of the distribution of the classes that we have. Then we have, obviously, some parts of the code. So this could be a homage to Python, Jupyter Notebooks, but also to GeoPandas, because this is heavily dependent on that. And then we start by actually calculating the point density, and we show statistics that we start from a high level, we aggregate them in different groups, and those groups are water, forest, artificial surfaces, and agricultural surfaces areas. And then we move on, and we start going deeper and deeper into the layers of the statistics that we produce, and we compare them with ascending and descending, which is related with the question from before, because basically what we want to guarantee is that across the different sites that we have selected, we get the same density, but also between the ascending and descending, we want to make sure that we don't see very big differences. So we start scratching the surface and going deeper and deeper into statistics. We provide statistics also for other metrics that are available in the dataset, so we invite the users basically with that to explore them. And here we make an intercomparison between the classes, the different land cover classes, and again between ascending and descending. And here it is the comparison between the classes, and here between the classes, but between ascending and descending. So the idea is here. The idea here is that whoever wants can take that notebook. They can focus on the level of analysis that they want to perform, but also they can play themselves with the data. And as I was saying, this is basically an aggregation of the results, and we have repeated that for the 12 different sites that we were showing before. So I will go again to the slide, which is over here. But the final user can download the data in a very accessible and fast way, as we saw before, and perform their own analysis. In our case, we collected the various results that we got from the 12 different Jupyter notebooks. We aggregated them, and we included them in our final report. But yeah, this is it. I invite you to explore the EGMS data, download them. You can go directly and check them in QGIS, but also visualize them and play with them and combine various products in a Jupyter notebook and explore whatever might be your interest.
Thank you very much, Joan and Amalia, for this interesting talk. We have time for a few questions. Are there any questions in the audience?
Thanks, looks really nice. I just had a question on the download, so I was wondering if you actually offer some kind of time series download. So if I select my region of interest, I'm sometimes not interested in images, but I'd just like to get the time series of all points in the area.
Yeah, so when you download the data, basically it includes the entire time series. So
yeah,
you
but
can...
as non-aligned images, right? So not as a time series per point.
It's a time, yeah.
Oh.
There is an API we will be working on, but for the next release. So, yeah, then you will be able to query directly instead of going through this download per burst that is now the first version. Yeah.
Thank you.
More questions? Yes.
Sorry if I missed it. Can I ask the temporal resolution? How often do you return to?
So, yeah, that depends because there was a failure in Sentinel. So, all the available Sentinel-1 images processed, so 6 days or 12 days, depending on the availability in that period, let's say.
More questions?
For the land cover classes, you use the high resolution layers of ESA. Sentinel-1 is not used as well for the high resolution layers classification?
You mean for the Urban Atlas, no? That is used, is part of the products used to generate Urban Atlas.
Can be Urban Atlas, I don't know.
No, we use Urban Atlas, which is a vector dataset land cover, which is validated as well to do the comparison. And it has those classes that Amalia presented.
Okay. But this Urban Atlas, it's also partly based on Sentinel-1? Or
It might be. I need to check the specs. Yeah. But so
I was wondering about how you manage the data, like interconnections, because now data are being it starts to be used like in many different products, and all the data are starting to get mixed with another, and it's difficult to get tracks. Like
so yeah, for instance, ground motion is extracted from the phase of the signal, and they probably use the amplitude for the line cover. So that's already two different things, but yeah.
Also, if I understand correctly, It wasn't very difficult in that case because the urban atlas are polygons, and then what we measure are the points. So we just count how many points fall within each polygon. So integrating the two data sources was not difficult in that case. Yeah.
Okay, thanks again, and applause for Amalia and Ortho.